to learn how to take the derivative using implicit differentiation today. And you need to be good at this before we go into 3.8, because you have to know how to do this before you can do the stuff in 3.8. So it's definitely a building process. Okay, so again, this is section 3.7. This is implicit differentiation. That's a big word. Differentiation. I don't know what that is. Differentiation. Whoever made up that word. You have to think about it when you write it down. And dot all those I's. Okay, so talking about implicit differentiation, talk briefly about how to calculate the derivative. Where we run into a little bit of an issue and why implicit differentiation becomes something a skill that we need. Well, going back to something we know, if f of x equaled something like, well, y, f of x and y are the same thing, okay, pretty much, then x, if it equaled x squared plus 5x plus 3, and they asked me to calculate the first derivative with all of our little shortcut rules, this becomes quite easy. It's just 2x plus 5, no big deal. But everything we've taken the derivative of so far has said y equals, which is the easiest way to take the derivative. But suppose we have the equation like x squared plus y cubed minus 9xy equaling 10, and they say take the derivative of that. It doesn't say y equals, and you know, I don't think we could solve that equation for y so that it said y equals, so that we could go in there and take the derivative. Okay, sometimes you can solve the equation for y, and sometimes you can't. And so we have to figure out a way to address this situation. So just very briefly, I'm going to show you a little bit of the trick, and pretty much you'll learn the pattern again and be able to use what we call implicit differentiation to take the derivative of such equations. So let's go to a little more basic an equation. So suppose x cubed plus y cubed equals 15, and we need to take the derivative of that. Well, we're doing dy dx, so the x variable is not a problem. So when you're doing dy dx, x is not a problem. It's taking the derivative of the y variable that you're thinking, how am I supposed to handle that? So it's this y cubed that gives, that makes us stumble here. So let's kind of look at this for just a minute. If you let y equal f of x, then y cubed would equal f of x cubed. Okay, so if we're looking at f of x cubed. So then, if we're trying to take the derivative, and let's not look at the y cubed part anymore, but if we want to take d dx of this f of x cubed, then it would be like the chain rule, where you would bring the 3 out front, you decrease the exponent by 1, and then take the derivative of what's in the parentheses, which we would rewrite as f prime of x. By the chain rule. Okay, by the chain rule. Well, if we want to look at it the way we normally see it, and it's not f of x cubed, it's y cubed, then the pattern is 3y squared, because f of x is y, f of x is y, and f prime of x is y prime. And this is what we'll do. Okay, we'll get rid of all the function notation that gets kind of complex in its appearance, and this is what we'll do. So the pattern is something like y cubed. When you're taking the derivative with respect to x, or d dx, then you pull the exponent out front, you decrease the exponent by 1, and you add the y prime on the end, which we often write as 3y squared dy dx. Okay, so we really shift back and forth between the y prime and the dy dx. And my prime looks like a 1, but it's more of an apostrophe, and it probably should be at a little bit of an angle. But so that's kind of how it works. So when we come back up here now with kind of this understanding of this little shortcut we're going to use, If we want to take the derivative of x cubed plus y cubed equaling 15, then if we do this, the derivative of x cubed, okay, the derivative of x cubed is 3x squared. The derivative of y cubed is where we're really throwing in this new implicit differentiation skill, which is a 3. Y, decrease the 3 by 1, and then dy dx, or y prime. And then the derivative of 15 is 0. This is a y prime. Now, the goal is, what is y prime? Up here we figured out what y prime was. We like to know what y prime equals. So when we have something written like this, we normally kind of solve it out so it says y prime equals. So to write this as y prime equals, I'm going to subtract 3x squared from each side, and then divide each side by 3y squared, and then lo and behold, the first derivative is a negative x squared over y squared of that cubic function. Well, it's not a function. Cubic polynomial, okay? So, because we're taking the derivative with respect to x, which is what this ddx stuff is all about. This means taking the derivative with respect to x. X is not a problem. Y is, okay? Y is where you add the y prime in when you take the derivative, which is what implicit differentiation is really teaching us today. Okay, so let's just go in and do some examples. You're going to kind of have to, you get kind of used to the flow of doing this when you've practiced it many times. So we're going to come in here now and do some examples and try to get comfortable with this new method. Okay, the goal is to find dy dx, which is the same thing as y prime. Okay, so suppose we have a very similar example to this one up here, but suppose it's something like x cubed plus y cubed equaling 18xy. A very similar example, but we don't just have a constant on the right side of the equation. We have 18xy, which is a product. Okay, so here we go. We're going to take the derivative. Okay, the derivative of x cubed is 3x squared. Here's a y variable, so we're going to really throw this implicit differentiation into this y cubed. So the derivative of y cubed is 3y squared dy dx, which I'm going to write as just y prime. Okay, how do you take the derivative of something like 18xy? Derivative of y is y prime. But how about the product rule, right? Oh, okay. Okay, here's the first and here's the second. Okay? So this is the first times the derivative of the second. And the derivative of y is really 1. And don't forget the y prime. Like the derivative of x is 1. The derivative of y is 1, but you've got to throw the y prime at this implicit differentiation. So this, I'm going to write 1y prime. Eventually, we're just going to write y prime. First times the second, plus the second, which is y, times the derivative of the first. Well, the derivative of the first has got the x in it, which is no issue, because we're taking the derivative with respect to x. So this is just 18. The derivative is now kind of calculated, but it's all in here. It's here and here. But let's clean this up. So this is 3x squared plus 3y squared y prime equaling 18xy prime plus 18y. Now I really need to solve it for y prime. So to solve it for y prime, I'm going to get all my y prime terms on the left and all my not y prime terms on the right. So in other words, this guy needs to move to the other side of the equation, and this one needs to move also. So the left side is 3y squared y prime minus 18xy prime, and the right side is 18y minus 3x squared. Now when I factor a y prime out so I can get y prime a little more alone, this becomes 3y squared minus 18x. And now to write it as y prime equals, y prime will equal 18y minus 3x squared over 3y squared minus 18x, which, you know, I think we could take a 3 out of every bit of that, couldn't we? So we took a 3 out of the top and a 3 out of the bottom, and this would be 6y minus x squared over y squared minus 6x, and that's what y prime equals. I took a 3 over a 3 or a 1. I factored something equivalent to 1 out of that rational. So honestly, I better never put 1 as an exponent anymore. So you can make certain you see these are primes. Why in the world am I thinking of transformers? What is his name? Somebody Prime. Optimus Prime. Optimus Prime. I do like the Transformers. My son is really, really into it. Okay, here's another one. This is weird. Okay, so this one says 3 plus y plus 7 squared equals 6x squared. And they want me to compute dy dx. Oh boy. Why in the world did they put... What did I do? I did it wrong. It is not 3 plus y. It is 3y. My mind is on Transformers. I should never watch TV and do calculus at the same time. Takes a lot longer. Okay, so here we go. This is definitely the chain rule. And the only thing I can tell you about a chain rule to remember when to do it is anytime you have a polynomial, often a binomial, to a power, that is the chain rule. Or a trig function is almost always the chain rule. So if I'm taking the derivative to the left side, I bring the 2 out front and decrease the 2 by 1, and then take the derivative of what's in here. Well, the derivative of 3y under implicit differentiation is what? 3, like if it was 3x, it'd be 3. But it's 3y, so it's 3y prime. Okay, the derivative on the right side is no big deal. There's no y over there. It's just x, and we're taking the derivative with respect to x, so that's just 12x. So we've really calculated the first derivative at this point, and that's an exponent of 1, which I said I'd quit doing, but I did it anyway, didn't I? Okay, and so now we need to solve it for y prime. So let's clean it up. 2 times 3y prime is 6y prime times 3y plus 7 equaling 12x. If I'm trying to solve this thing for y prime, what am I going to do? That's right, and the 6, right? Get my pencil. If I divide both sides by 6 and 3y plus 7, right? That's what's going to leave behind the y prime. So then I have y prime equaling 12x divided by 6 times 3y plus 7, but the 12 and the 6 will reduce. So y prime is what? 2x over 3y plus 7. By implicit differentiation. So from this step to this one, I don't know, you need to tell yourself what you're doing. We're taking the derivative all of a sudden. Okay, when you start seeing that little prime in there, you're taking the derivative. Well, let's try another one. Suppose we have x to the 4th plus sine of 2y equaling x cubed. They asked me to take the derivative with respect to x. Okay, with respect to x. So the derivative of x to the fourth, that's no big deal. That's just 4x cubed. This derivative of sine 2y, there's your y variable. Okay, the derivative of sine theta is cosine theta, really d theta. So the derivative of sine 2y is cosine 2y times what? The derivative of 2y, which if it were 2x, the derivative is 2, but since it's 2y, it's 2y prime. That is really the chain rule being applied to a trig function. Then on the right side of the equation, the derivative of x cubed is 3x squared. So we need to solve this thing for y prime, so subtract the 4x cubed off. So this is a 2y prime cosine 2y equaling negative 4x cubed plus 3x squared. And then solving for y prime, you would divide off 2 cosine 2y. So it becomes, the 2's will go and the cosine function will go. And so it becomes y prime equaling a negative 4x cubed plus 3x squared over 2 cosine of 2y. Bless you. Mm-hmm. Mm-hmm. Product rule. Yep, I guess that's a good way for me to try to explain that too, is you got both variables next to each other. That's a product rule. Okay, two variables. Mm-hmm. Take it out, factor out the x. You can't just take it out. It's like taking down. You really can't. I don't think you can do what you're wanting to do.
Take it out, but you have to put it in parentheses on the side.
That's right. Taking it out means factoring it out, which is still part of the picture. It's not gone. Then it becomes the product rule even worse. Okay, here we go again. This one's interesting. Suppose it says cosine of 2x plus 3y equaling y sine of x. We're going, boy, I hope I remember how to use all my trig rules, right? There's a left side and there's a right side. Okay, and really, on the left side, the derivative, if this were theta, the derivative of cosine theta is a negative sine theta, d theta. Okay, so the derivative here of cosine theta would be a negative sine theta, where theta is 2x plus 3y. But then you come back and take the derivative of theta. So you take the derivative of 2x plus 3y, which is, the derivative of 2x is 2. The derivative of 3y would be 3y prime. Okay, on the right side, somebody tell me something about this y sine x. How are we going to do this? The product rule. It's kind of like saying xy, the thing with the thought of two variables being a product of, you're going to have to use the product rule where y is first and sine x is second. So first is y, derivative of second, the derivative of sine x is cosine x. The second is sine x, and the derivative of y, don't just put 1, but put what? Y prime. So we have formed the derivative. Now we just got to clean this thing up and solve it somehow for y prime. Well, let's think about this for a second. Study this out. That's right. Okay, so the right side is no big deal. We can figure that out. What are we going to do on the left side? We're going to have to multiply out this 2 plus 3y prime to get the y prime out of the parentheses. to isolate on the left side of this equation. And don't forget this little negative sitting over here. So when I distribute the 2, it's going to be the negative times the 2, sine of 2x plus 3y. And when I distribute the 3y prime, don't forget the negative. So it's a negative 3y prime sine of 2x plus 3y. Okay, so here is a y prime term, and here is a y prime term, and I'm going to move them all to the left and move everything else to the right. So now I have a negative 3y prime sine of 2x plus 3y, bring this y prime over, which is a subtraction of y prime sine x. Then on the right, I have a y cosine x, and move this 2 sine 2x plus 3y over. There we go. Definitely looks like a foreign language. Looks like a major mess on my piece of paper, doesn't it? If I was watching Transformers and got distracted and looked back, I'd have to really think for a minute what's going on this piece of paper. Okay, so now factor out a y prime, and it's going to leave behind a negative 3 sine of 2x plus 3y minus sine x. And then divide it off. Then divide all of this off of y prime. So you're going to take a negative 3 sine of 2x plus 3y minus sine x off of each side. It's like, woohoo! Say, please don't ask me to graph this thing or to evaluate it for any reason. Okay, y cosine x plus 2 sine 2x plus 3y. And at this point you're saying, please tell me I am done. The only thing that they would ask you to do is factor that negative out of the denominator. So if you have a multiple choice question, you would check for that. Or multiple choice options for the answers to your question. Okay. Now remember, all these y primes can be replaced with dy dx's. So if you're, I'm not certain what, if you're looking at the answer or whatever in my math lab, this step right here, in place of that y prime, they could have dy dx. Everywhere there's a y prime, dy dx is the same notation right there. So don't let that, throw you off in any way. It's just another way of writing it. Okay, so now what can they do to me? We figured out, well, we're still using implicit differentiation. Implicit differentiation. That is a big old word to have to write. Differentiation. Okay. So the first dy dx is our y prime. And d2y dx2, which is what? Y double prime. Second derivative. Y'all don't look too happy about that. I'm not getting pleasant, joyful expressions. Okay, and you know what? This does require a lot of space, so I'm going to turn to the next page. You might want to be at the top of your piece of paper, too. Okay. So here we go. Find y prime and y double prime using implicit differentiation. And it's y squared equaling x squared plus 2x. That's a squared, not a cubed. It's a squared. My pen kind of made it look like a 3. Okay, so first derivative. Here we go. Y squared is 2y, y prime. First derivative. The derivative of x squared is 2x, and the derivative of 2x is 2. That's not so bad. So y prime is 2x plus 2 over 2y. We can take a 2 out of everything, right? Remember, if you factor out a 2 on the top, you factor out a 2 on the bottom, then your first derivative is x plus 1 over y. That wasn't so bad. Okay, so there's one of the answers. Now, y double prime. Quotient rule, right? The bottom is y times the derivative of the top. The derivative of x is 1, and the derivative plus 1 is 0, so it's 1 plus 1, which is 1. Bottom times the derivative of the top minus the top, which is x plus 1, times the derivative of the bottom. The derivative of y is 1, y prime. All divided by the bottom squared, which is y squared. Okay, so this equals what? Y minus let me think about this a second. How do I want to do this? I don't think, do I want to distribute that in there or not? I don't think I want to distribute. So I'm going to leave it as x plus 1 times y prime over y squared. But we're not done, because y prime equals up here this x plus 1 over y. So this becomes y minus x plus 1 times x plus 1 over y all over y squared. That's not bad. Okay, and in that numerator, I need a common, well, I guess I'll write another step. So this is y minus, what, x plus 1 squared over y, all over y squared. Now, in the numerator part of this complex fraction, if I want a denominator of y, then I'd have to multiply this times y over y, right? Y over y, which is equivalent to 1. So this becomes y squared minus x plus 1 squared over y squared over, it's just y, not y squared, over y squared. Then, if I multiply this times 1 over y squared and this times 1 over y squared, because the 1 over the y squared over the 1 over the y squared is 1, so I'm still multiplying by something equivalent to 1, then this becomes y squared minus x plus 1 squared over y cubed. And I think we're done. Because remember, all this cancels, right? This cancels and this cancels, so you're only looking at this part at this point. And y times y squared is y cubed. Oh, y'all get good at this. We'll do another one. We'll take a break because we're not through with this section. Y'all look like y'all definitely need a break. Ms. Zachary is rolling right along. Wow, this next one's interesting. Okay, y'all better watch me close. Make certain I don't make a mistake on this one. This would not be fun to make a mistake on this one. all these rational exponents. Okay, here we go. Take the first derivative. The first derivative is 2/3 x to the 2/3 minus 1, which is 2/3 minus 3/3, which is a negative 1/3. The derivative of y to the 2/3, bring the 2/3 out front. Y to the 2/3 minus 1, which is 2/3 minus 3/3, which is a negative 1/3, y prime. The derivative of 1 is 0. Solve this thing for y prime. So we subtract 2/3 x to the negative 1/3 from each side of the equation. Then, this is interesting. That's what I was going to say. I guess that's what I'll write. Divide by 2/3 y to the negative 1/3, right? Divide by 2/3 y to the negative 1/3. So then you have y prime equal to the 2/3 over the 2/3, or the negative 2/3 over the 2/3 is negative 1, right? So it's a negative x to the negative 1/3 over y to the negative 1/3. Which is the same thing as a negative y to the positive 1/3 over x to the positive 1/3. No. Well, when you move them, they become positive, okay? And this is a negative cube root of y over a cube root of x, which is the first derivative. Okay, that's the first one. So I think this is the version I would go with when we take the second derivative. Maybe. Maybe not. Maybe I would write it x to the negative 1/3, y to the positive 1/3, and I would use the product rule to make the next derivative. So this was the best answer. This is what you would answer in my math lab. Okay, the cube root version is what you would type in my math lab. To get ready to take the second derivative, I think this is what I would do in order to then apply the product rule, where the first is x to the negative 1/3 and the second is y to the positive 1/3. So here we go. The first, which is a negative x to the negative 1/3, times the derivative of the second, which is 1/3 y to the 1/3 minus 3/3, which is a negative 2/3, 2/3 y prime. That's the first times the derivative of the second. Plus the second, which is y to the 1/3, times the derivative of the first, which would be a positive 1/3 x to the negative 1/3 minus 1, which is a negative 1/3 minus 3/3, which is a negative 4/3. Oh, God. Oh, my. Okay. But this guy gets replaced with this. Right? So let's clean it up just a little bit before we do that substitution. This is, I'm going to pull the 1/3 out front. Negative 1/3 x to the negative 1/3, y to the negative 2/3, and then y prime is a negative x to the negative 1/3, y to the 1/3. Okay, so this is a negative times a negative is a positive 1/3. X to the negative 1/3 times another x to the negative 1/3 is x to the what? this x times this x is x to the negative 2/3. Right, negative 2/3. And then you have, no, because this negative times this negative made it positive. Okay? And then with the y's, a negative 2/3 plus 1/3 on this exponent is a negative 1/3. Oh boy. Now there is a GCF. Okay. And the GCF is 1/3 x to the negative 4/3 y to the negative 1/3. That's your GCF. So on the first term, you pull off the 1/3, and x to the negative 4/3 times something is x to the negative 2/3. So what is it? It's another 2/3, right? And you already have y to the negative 1/3, okay? So then the second one, you pull the 1/3 off, y to the negative 3rd times y to something, and it would be 2/3. And you already have the x. Okay, so we're pretty much in the answer format now. We are very close. These guys must go into the denominator to make them positive exponents. So the denominator is 3x to the 4/3 y to the 1/3. The numerator is x to the 2/3 plus y to the 2/3. And I think that's good enough for me. They might want you to put it back into a radical format, but here's kind of the trick to that. They didn't start with radicals. They didn't give me radicals initially, so I should be fine leaving the answer without radicals. Okay, now we're not through with the section, but let's take a break. Okay, so let's go ahead and finish this. Find that screen again. There it is. Okay, and enlarge it. And where are my glasses? There they are. Okay, so part C. I think y'all might like this part. Okay, examples. Okay, of slope and tangent line. Yeah, something a little different. Okay, slope and tangent line to the curve. Okay, and I'm taking this one straight from the book, so if you ever want to go back and reference the textbook, this is example 2 in the textbook on page 150. And here's the question, and it says, find the slope of the tangent line to the circle x squared plus y squared equaling 25 at the point 3, negative 4. Find the slope of the tangent line to the circle, or the curve, which is a circle, at the point 3, negative 4. So we kind of want to get a vision of this. This is a circle centered at the origin whose radius is phi. Oh, and I don't make circles well. 1, 2, 3, 4, 5. That's pretty good. At the point 3, negative 4. 1, 2, 3, 1, 2, 3, 4. Right there. So we want the tangent line to the curve at that, well, I guess the top right quadrant doesn't look so wonderful on my circle, but could be worse. Pressure's on underneath this camera. So here's what we're looking for, is the slope of this line. Okay, so the curve is x squared plus y squared equaling 25. The derivative with respect to x is 2x plus 2y dy dx, or y prime, equaling 0, because the derivative of a constant is 0. So your goal is to solve this for y prime. So this is 2y y prime equaling a negative 2x. So y prime equals a negative 2x over 2y, which is just a negative x over y. Now remember, y prime is the same thing as the slope of the tangent line anywhere on the curve. So this is the slope of the tangent line. Y prime is the slope of the tangent line. So now if I want the slope of the tangent line at the point 3, negative 4, what do? Plug it in, the x and the y. That's the change, is we have an x and y variable. So it's a negative of a 3 over a negative 4, which is the slope of a positive 3/4. And our sketch looks, that's probably right. They were probably good. Now, they didn't ask, but had they asked for also the equation of the tangent line, which they're definitely going to progress into this, if they ask for the equation of the tangent line at that point, then your point is 3, negative 4. Your slope is 3/4. So y minus y1 equaling m times x minus x1 becomes y minus a negative 4 equaling 3/4 times x minus 3. Get back up on the camera. So y plus 4, so this is 3/4 x minus 9/4 minus 4, or the equation of the tangent line to the circle, or of the tangent line to the curve, is 3/4 x minus, what, 25/4? Okay, not bad. Okay, so here comes another one, which would be number 2 under part C. Okay, this one is example 5 in the textbook, and I did not put the page number, I apologize. But this one says find the I'm going to change it. Find the, do I want to, how much do I want to do? No, I'll do it. Find the equation of the tangent line and the normal line to the curve, and the curve this time is x cubed plus y cubed minus 9xy equaling 0 at the point 2, 4. Find the equation of the tangent line and the normal line to the curve at the point 2, 4. What is a normal line? No, normal is perpendicular. Y'all remember that? Normal is perpendicular. So the normal line to the curve would be a perpendicular line to the tangent line. Okay, so it's perpendicular. So here's the curve, the equation of the curve, and let's find dy dx. First derivative. So it's going to be 3x squared plus 3y squared y prime. What about this 9xy business? Product rule. So it is the first, which is 9x, times the derivative of the second, which is y prime, plus the second, which is y, times the derivative of the first, which is a 9. I've got to figure out what to do with this minus sign here. This case it's a 9x, okay? I pulled the minus out front, so I'm just taking the derivative of 9xy. I pulled the minus out. Is 9. Okay, thank you. And the derivative of 0 is 0. So this is 3x squared plus 3y squared y prime minus 9xy prime minus 9y. Your goal is to find y prime. So move the 3x squared and the 9y, which is a 9y minus 3x squared, to the other side and factor the y prime off of the 3y squared and the 9x. Skipping a step or so there. So then y prime is 9y minus 3x squared over 3y squared minus 9x. So I can take a 3 out of the top and the bottom, leaving behind a 3y minus x squared over a y squared minus 3x. There it is. And now, think about this a second. Y prime is dy dx, which is the slope of the tangent line anywhere along this curve. So this is the slope of the tangent line anywhere along the curve. So the slope of the tangent line at the point 2, 4, because that's where they asked me to do this, at 2, 4, the slope at 2, 4, using this 3y minus x squared stuff, is 3 times a y value of 4 minus 2 squared over y squared, which is 4 squared minus 3 times 2. So it's a 12 minus 4, which is 8, over a 16 minus 6, which is 10. So this is 4/5. That's the slope of the tangent line to the curve at the point 2, 4. Okay. Okay. So now if I want the equation of the tangent line at the point 2, 4, whose slope we just found out to be 4/5, it will be y minus y1 equaling slope times x minus x1, which is y equaling 4/5 x minus 8/5 plus 4. Pull the 4 over. So it is 4/5 x, what, plus 12/5? Okay, there's one of the answers. The next question is, what is the equation of the normal line to the curve at 2, 4? Well, what's the slope of the normal line to the curve at 2, 4? There you go. If this is your tangent line's slope, then your perpendicular line to the tangent line will have a slope of the negative reciprocal, which is a negative 5/4. So its slope is a negative 5/4. Slope of the normal line to the curve. So its equation will be y minus y1 equaling slope of a negative 5/4 times x minus x1. So it's a y equaling a negative 5/4 x plus 10/4 plus 4. Well, 10/4 is 5/2, 4 is 8/2, which is 13/2. Did I get that right? There's the normal. Now there is a picture of this in the book. I wanted y'all to see it. If I can find it, here it is. It is on page 152, so if you want to write that down, example 5. Page 152. This is what it looks like. Here's the curve. This is the graph. What was all that? Oh, here it is. Some of my recording stuff. State. Okay. Here is the curve. The blue line is this curve. X cubed plus y cubed minus 9xy. This is that graph. And the point right here was 2, 4. And this red tangent line is what we came out to be 4/5 x plus 12/5. And the green normal line to the curve is the negative 5/4 x plus 13/2. Yes?
Is there a way you can graph that on a calculator?
Let me look at it. Not on the 83 or the 84, but I think on one of the higher ones. Yes, I think you can. Yeah, I've seen it done on a calculator before, so it was one of those bigger ones that would take me a while to figure out how to operate. Okay, that is actually the end of the section, so let me give you all your quiz. But it's a take-home quiz. So I want y'all to get started, definitely started in here. Okay, I don't want you to leave too, and this is what's awful. My copy machine ran out of paper, so I went to the other copy machine and it ran out of staples. So, I did stop recording, right? Before I wander about this room, let me double check.